Responsive dehydration, sensor-driven optimization of production cycles in a solar dehydrator. Drying is one of the best methods for food preservation. Alternative to freezing, it consumes less energy with equivalent results. Moisture removal has high heat costs. For example, a ton of coffee requires 21.10 gigajoules to be spray dried. This consumption is nearly half of a standard European household's heat yearly. These high energy costs are added to the equipment costs of industrial machining, making it hard for the smaller producers to compete in the drying food market. This article presents a piece of equipment in the state of experimentation validation that approaches this high-cost problem in a sustainable and high-tech way. It can work with a mix of 400 kilograms of product divided into bags of 10 kilograms each. The main instruction is made of aluminum and covered with a tarp like a tent. It is a solar dehydrator that has one solar collector, one chamber, and one chimney. It was made for acorns, the main raw material of the partner company. Its objective is to make a pre-drying for better conservation and to reduce the energy cost in later industrial processing. It works as in the following picture. The collector has an opening at its bottom chamber faced wall. Since the collector is heated by sunlight, the air inside will expand and rise. New ambient air will enter the cavity by the differential pressure created to generate airflow. The chamber has one opening on its top front wall, where the air from the collector will enter. As the air flows inside, it will pass through the bags, carrying out the moisture as the water vapor leaves the food. The air temperature cools, increasing density. The colder air will flow to the bottom and be expelled to an opening at the bottom of the back wall. The chimney has one opening at the bottom of its front wall, where the air from the chamber will enter. Its top part changes from a square section to a triangular one, decreasing the area and increasing the airflow velocity. As the section area falls and the top black part is heated by sunlight, the hot air is expelled through the self-adjustable windwheel chimney hood. This process continues as long as there is a temperature difference between the heated source and its surrounding, driving the natural convection flow. The equipment was instrumented with sensors to measure temperature, humidity, radiation, and load. The radiation sensor is located on the chamber's roof, away from the chimney, to avoid shading problems. The instruments that allow the proof of concept validation are powered by a battery charged by the photovoltaic panel. In total, there were 17 temperature/humidity sensors, and one for each other type of sensor. In the left picture, it can be seen the monitoring sensor devices inside the main chamber. And in the right one, it can be seen all the positioning of the temperature/humidity sensors that are on the equipment. The data can be monitored in real time by a custom-made application. In the picture below, the main interface is displayed. At the main screen, it is possible to verify each sensor's temperature and humidity, as well as the product total weight. At 22.06 kilograms and sun radiation of 309 watts per square meter, with this information, the operator will know when to collect the product based on the difference in mass notified by the pregnant via smartphone, smartwatch, or personal computer. Different values for temperature are displayed. Such a difference happens because the collector and chimney are receiving sun radiation, while the drying chamber gets cooled down by the evaporative cooling. In the picture, the highest temperature is from the sensor at the top of the windwheel chimney hood, and the lowest is from the middle inner of the chamber. The three charts at the center display some of the sensor's daily values. The sensors were installed to optimize production. They are connected to a data acquisition and sharing system, which aims to notify the operator about the right time to collect the food and changes the bags for new produce. The main goal is to avoid any unnecessary waste of time and resources. By avoiding collecting the food too early, before reaching the desired dryness level, the system guarantees a sustainable way of constantly supplying the same product quality and mitigating wasted time and resources. Alternatively, it also avoids the late arrival of the operator, guaranteeing the product is not overdried. The extra drying time can be then used for a new batch of products. The conditions inside the chimney and drying chamber and the weight loss measured throughout the drying process allow us to confirm that the equipment operates as designed. The drying process of this prototype resides in two phenomena. One, the increase in temperature, which in turn dries the air. And two, regular air circulation generated by the hot air produced in the collector, which goes to the drying chamber and subsequently to the chimney. The results of this first phenomenon are in the figure. This graph simultaneously shows the evolution throughout a typical November day of solar radiation, G, and temperatures inside the drying chamber, T2, in the chimney, T1. The radiation scale is represented on the left ordinate, and the temperature scale on the right ordinate. The day was sunny, with sunrise around 8 a.m. and sunset at 4:45 p.m. The irradiation value is null outside these times. There is an increase in radiation throughout the morning until reaching the zenith at noon, with maximum value of 600 watts per square meter. At the same time as the radiation increases, we have an increase in the temperature inside the chamber from 2 degrees Celsius at 8 a.m. to 22 degrees in just 1 hour. The increase in temperature is even more pronounced in the chimney, rising from 2 degrees Celsius to 30 degrees Celsius in the same period. This temperature difference is responsible for air circulation between the bags filled with acorns, promoting their drying. This drying is more delicate as is done at a low temperature, which does not exceed 40 degrees Celsius throughout the day. Note that the temperatures in the drying chamber remain high throughout the day, even with lower radiation values. This figure shows the expected result over 3 days of drying. As the acorn bags lose water, they begin to become lighter. The product weighed 22 kilograms in the graph, indicating that the bags were too full. Drying proceeded normally, although at a slower rate than initially forecasted due to the desiccation characteristics of this type of acorn. Aside from the communication resort, a production control system was also implemented. It provides production control through barcodes on each bag, allowing control from drying to the factory. The bags leave the dehydrator and are transported to the factory, enabling trackability with the producer, the species and tree coordinates, delivered mass, drying percentage, and harvest date. The barcode can be seen in the upper part in the picture. Every time a bag is hung, its barcode should be scanned to enter the information into the system. Through this logistic, one obtains better production control, accelerating the in-factory identification processing process by simply checking the bag. Implementing monitoring systems in low-tech solar equipment can be a powerful combination. The simplicity, low capital, and operational costs make this an excellent way for smaller producers to compete in the food industry. Of course, just like any new technological development, improvements are needed. The drying rate did not reach the initially forecast because of the minor problems in the dryer related to the bag's overloading and acorns' desiccant properties. Moreover, telemetry was a success. The data could be consulted in real time via the internet. This system allows for flagging when the predetermined dryness level is reached. Also, the barcode mechanism promises to improve the whole value chain of the product as production grows. Future work should mainly address the feedback of the sensors to the user. Data collection and storage should be optimized, avoiding wasting time and computational resources when reading and breaking down data. The design of an interactive application for reading data, graphs, and reminders for the operator will be one of the main objectives in the future, thus facilitating the dryness process for the operator. With the following authors, with the financial support of La Caixa Foundation and partnership with Landratec.